Hello guys, so in this video I'm going to again explain image filtering in frequency domain, but this time we'll also see the Gaussian filter. So basically I have explained the whole program in this video. I'll put the link in the description, as well as if you click over here you will see the video link. So here I have explained the program line by line, so you can very well understand it from here. And now what I'm going to do is I'm going to actually execute these in Matlab, and we'll see exactly how does the outputs over here look like. Okay, so let's first execute this program, and then we'll see the Gaussian case. Okay, so instead of an ideal filter which is over here, what happens if we have a Gaussian filter? That is what we are going to see next. Okay, so I have typed the code over here. Let us just execute it one by one so that we get a better understanding. So the first so I've changed the code a little bit, so that I can make it more user friendly. So the first part over here, this part is to open a window so that you can choose any image from your folder that you want to run the code with. Okay, so for now let me run with this image. Okay, so this particular line of code just accepts the image, and you can see that there is an im read over here. So whatever file it gets with this ui get file, so the window that you saw was because of this, and that file location, the path and the file name is put into f1, and that you can see over here. Okay, now next what it does is clears anything else that is not a, because a is our file name, that is our image, and others we just remove that. So now I'm going to step by step execute this program, so that one second, yeah, let me put it over here, and then we'll see that how does every line function. Okay, so over here you can see that all the variables except a are deleted over here. Okay, so this is just to become more to give ram to just free up the ram. Okay, so now convert to grayscale in case it is color. So now you can see that this is a color image because it has three-dimensional matrix. So hence here you can see if size of a, so that means size of a is this 624 into 480 into 3. Now the size of a, that is size of this thing. So just to give you a good visualization, so the size of a is this thing 64 483. Now if I do size of a, I get 1 comma 3. Why 1 comma 3? Because it takes the size of this thing. So this has one row and three columns, so hence 1 comma 3. So if it is a color image, then what will happen, this will be 1 comma 3 because there will be three dimensions. But if it is a grayscale image, then it will have only two dimension, it will not have this dimension. Hence what I do is, if size of a is equal say a comma 2, so why 2? So this is 1, I mean comma 1, let me just do that as well. So if I do comma 1, I get the first number. Okay, if I do comma 2, I get the second number, that is 3. Okay, so if it is a color image, this size of a comma 2 will be equal to 3. That means it is a color image. So then we can change it to grayscale. Okay, so here it is a color image, hence it has gone below, that is it has entered the if else loop. Okay, so now over here it will become grayscale. So now you can see that it is a grayscale, a two-dimensional image, and we'll go ahead. Okay, so the first thing is im2 double. So I had explained nicely in the previous video why we use im2 double. So basically what it does is it will now put all the numbers in the range 0 to 1. So now you can see everything is in point. So initially a was from 0 to 255, but now it is from 0 to 1. So this is what IM2 double does. It changes the range from 0 to 255 to 0 to 1. Okay. So now just let us subplot this image. So this is subplot function is to just create the axis in a figure, and then you do IM show A. So I'm just plotting the original image and I'm giving a title. So here you can see that the original image is plotted over here. So now there is 2 comma 3 comma 1. So that means now there will be 2 rows in this subplot and 3 columns. So 2 comma 3 comma 1. Okay, this is just the way how subplot works. Okay, here I take the size of the image. So M will have 624 and N will have 480. And now, so there was this one doubt that what should be the D0 input that we have. So the D0 input should be the half of the minimum of the two. I'll tell you why is this the case, but for now let us just go with it. So I have put that into this code as well. So what I say is enter the cutoff frequency. So what is the cutoff frequency? It should be a number that is less than 240. How did I get 240? It is just the minimum of the two, that is 480 divided by 2. So 480 divided by 2 is 240. I'll say why is this the case. So say let us just enter 50 for now. Okay, so this is a image of size this much. You take the minimum size and divide by 2. I'll tell why is that the case. Okay, so over here I've got 50. My cutoff frequency, that is my D0, is 50. Okay, so okay, now I'm going to do FFT, so the two-dimensional FFT. So in A I've got the complex value. So remember, Fourier transform always can give you complex values also. So now this capital A is the complex value or the Fourier transform of the image A. Okay. Now we can also subplot this, but now to show this we cannot show a complex image because it will need 4 axes then. So for now I'm just plotting the magnitude of this complex image. Okay, and the title is without shift. So till now I have not shifted the Fourier transform. So hence you can see over here. So this is what a Fourier transform looks like of an image. So it has a lot of energy over here in the corners, and in the middle it is almost black. That is, it does not have more energy or more value or more amplitude over here in the middle. All the amplitudes are in the sides. Okay, let us go ahead. Now we are going to shift this. So it is not easy to filter this kind of an image because then you will have to design a filter which is in the side. So then what we do is we shift this so that all of this information comes in the center of the image. So that is what we do. Okay, so there is this command FFT shift. By that we can do that. So FFT shift. Now if we just see what is the output. So A1 has the FFT shift of A, and then I've just done ABS of A1. So the magnitude of A1 is over here, and let us see that. So there's subplot, IM show, title. Okay, so now you will see in the third subplot I have the Fourier transform of the original image after shift. So you can see before shift the values were like this. After shift everything has come to the center. So now it is easy to filter. Now I can just have a filter from the center, and if it is a circle, so if I have an ideal low pass filter, I'll have a circle, and whatever is inside I'll accept it, whatever is outside I'll reject it. So that is the simple case. Okay, so this is just pre-allocation from memory. So I have a low pass filter that is going to go in A low, a high pass filter that is going to go in A high, D is for distance. And so this particular loop I have explained nicely in the video. So please go through the video for the explanation of this loop. So it is very simple. It is regarding the circle. So we just put in circle as an ideal low pass filter. So if whatever things are there inside the circle will remain, and all the values outside the circle will become 0. So that is the main purpose of this for loop. Okay, so for now let me just go quickly to this subplot. So for that I press continue. So this will take a little time because there are two for loops which are scanning the image for I is equal to 1 to m and for j is equal to 1 to n, and there is this distance that we calculate. So basically till the code runs I can explain you this. So what are we going to do is, okay, so that has done. So basically what are we going to do is we are going to find the distance from the center of the image to every pixel, and we are going to see if it is less than a particular threshold, that is d0. So that's what we do. Okay, so here let us yes, so this is about the filter that that I was talking. Let us just see the filter. Right, so this is the filter. So this is the ideal high pass filter. Now what we mean by that is, so I was talking about the circle. So there was this d0 input that we took. So this is the center of the image and d0 is the radius. Okay, how far you want the filter to be. So from the center, d0 is the radius. So for now what I did is I took 50. So my input over here was 50, that is 50 pixels. So from the center of the image, so if this is the center of the image, it is making a circle of radius 50 pixels. Okay, now this is the high pass filter. High pass filter means that anything outside this circle will be preserved and anything inside the circle will get lost. Okay, so all the values over here are 0 and all the values over here are 1. So what happens is when I multiply this filter with this Fourier transform, what happens is all these information is lost and I only get the outer information, that is this outward part, and that is what we call as the high pass part, because this is the low frequency and these are the high frequencies. Okay, so that is the motive of a high pass filter. Now the low pass filter is the opposite of this. For the low pass filter what happens is, here there will be one, that is this will be white and this will be black. So whatever is inside will be preserved and whatever is outside the circle will get lost. Okay, so that is the low pass, ideal low pass and ideal high pass filter. Now coming to why is this number 240. So this is like this. So this is the radius, right? So the radius from the center of the circle. Now this radius can be maximum this much, because if the radius is more than this, it will go out of the image. So hence the maximum allowed input is this, is of radius this much. So why this? Because so this is the 640. I mean that is one size of the image. What is that? 624 and the other is 480. So this is 624 and this is 480. So we can only go up till 480. That is the radius, the diameter of the circle can be maximum 480. You cannot go more than that because then you will go outside the image. So hence the radius becomes 480 by 2, that is 240. So hence the maximum allowed frequency that you can have for d0 or the radius is the whatever is the minimum size, whatever height or width, whatever is the minimum, you take the half of that. So that you can fit the circle inside the image. That's the only reason. Okay. So that was about why did I take this like so this is the highest possible frequency that you can have, but you can enter any number between 0 to 240 over here. That's okay. Coming back to the code, so now we saw that initially we over here we did shift, that is we shifted from the frequency contents were at this side and then we shifted these to the center, right? So hence we'll have to reshift them to get back the original image. So we are reshifting it. Then we are doing inverse Fourier transform. So this is the inverse Fourier transform, and we are taking the absolute of that because this is also complex value. So b1 if you see is a complex value. So again you'll have to take the absolute so that you get the real component, real values, and then just plot that. Okay, so here I'll plot the low pass first and then I will plot the high pass. Okay, yeah, so the code is done. Right, so here I have all the plots. So this is the low pass image of the original image, low pass content of the original image, and this is the high pass content of the original. So now there is one problem with this ideal high pass filter or ideal low pass filter, that it is a sudden cut. That is, here everything was 1. So for ideal high pass everything was 1 and suddenly everything became 0. So there is a very abrupt cut at this particular point. So suddenly everything has changed. It is not a smooth change. So because of this we see an effect which is known as a ringing effect. So over here you can see this is the original image. So here you can see there is no rings formed over here, but if you see the low pass, you can see rings over here. So this is something unwanted. This is something that the program did or the filter did. So this is a bad output because it is having these kinds of uh, abnormalities. Okay, you can see the same thing in high pass image as well. So if you see these rings over here, you can see this thing. So these things are the ringing effect, which is because of this abrupt change in the filter. So to avoid this, what one can do is we can use the Gaussian filter. So let us go to the Gaussian filter. So now instead of using the ideal filter, we'll see what a Gaussian filter can do. So the code is very similar. So for Gaussian filter, what we have to do is we have the formula for Gaussian. So that is e raised to minus the the distance, e raised to minus x. So there is this distance, and yeah, so I've just split it into two parts. So because this is a bivariate Gaussian function now, so there'll be x part over here, I minus m by 2, and there is a y part over here, j minus n by 2. And so this is the Gaussian filter. The basic Gaussian formula is what I've used over here. And now what we are going to do is we are going to multiply the frequency response, that is this image. We are going to multiply this image with not an ideal high pass filter but a Gaussian high pass filter, which is going to be smooth at the edges. So let us see that. So I'll just, so other parts of the code are very similar to this code, to the code that I just explained. Only I have put this Gaussian filter. That is the new thing that is over here. Okay, so let me just run this code. Again, it will ask you what is the cutoff that you want. So I can put the same cutoff for now. And yeah, and d0 over here is nothing but the variance of the Gaussian. How wide do you want the Gaussian to be? So that is d0 over here. Okay, so over here I have made a comparison. So I've done subplot such that I can compare the two. So this is the Gaussian high pass filtered image and the ideal high pass filtered image. So over here you can see that there is no ringing effect if you just compare. So over here you can see these small rings that you can see over here, but the same thing cannot be seen over here. So hence you can use Gaussian filter, that is much better than the ideal low pass or high pass filter. So you can see these rings a lot of there. Okay, so that was about high pass. Now this is the Gaussian high pass filter that I have used. So here you can see the smooth variation. So this is white and there is this gray, so smoothly it is going towards black. So that is the difference between an ideal high pass, which is an abrupt change from white to black, and this is a smooth change. Okay, so this reduces the ringing effect. The same thing you can see for the low pass. Here you can see there are no rings that are formed, but here you can see a lot of rings that are formed. Okay, so that is on low pass. And then over here the same thing. So this is the Gaussian low pass where these things are black over here and slowly they become white, and this is an abrupt change. Okay, and this is the original image and the frequency domain of the image. So that was about why Gaussian filter is better than this ideal low pass filter. And that's all for this video. Thank you so much for watching. Thank you so much.